Today, we continue to study Calculation 2. Let's study Section 9.3 together, the positive series, the integral test. Firstly, we focus on the following two issues. As two series, the summation of a times q to the power n, the summation of 1 over n to the power p, are they convergent or not? Firstly, look at the following new definitions. The summation of un. Un is non-negative, which means positive term series. Secondly, we try to find out the necessary and sufficient conditions for convergence. For S1 less than or equal to S2, less than or equal to Sn, namely monotonically increase. Only two conditions need to be satisfied. Condition 1, if n tends to positive infinity, Sn tends to positive infinity, which means the series diverges. Condition 2, the partial sum. Sn has upper bound, namely Sn is less than or equal to mu. Mu is some positive constant. Equivalently, the limit of Sn is S. Next, let's study the fundamental theorem. The positive term series converges if and only if the partial sum Sn is bounded, which means Sn has an upper bound. Pay attention to the following facts. The positive term series can be arbitrarily added brackets. Its convergence or divergence is invariable. If the positive term series converges, then its sum does not change, namely has the same sum. Look at example 1. Discuss the series, the summation of 1 over 2 to the power n plus 1 converges or not. Apply this inequality. 1 over 2 to the power n plus 1 is less than 1 over 2 to the power n. So we have the following sum. Sn less than 1 over 2 plus 1 over 2 to the power 2, term by term, finally equals 1 minus 1 over 2 to the power n, obviously less than 1. By theorem A, the positive term series converges. From the question, we can obsolete the factor to determine a positive term series is convergent or not. We can compare it with another convergent or divergent positive term series. We continue to study theorem B, integral test. Let f be a continuous positive non-increasing function on the interval 1 to positive infinity, half-closed and half-open interval, and suppose that ak equals fk for all positive integers k, then the infinite series, the summation of ak converges. If and only if the improper integral converges. We continue to study theorem C, pay attention to the given condition. If un is less than or equal to Vn and non-negative, we will have the following two important properties. Case 1. If the summation of Vn converges, then the summation of un will converge to. You can think it in another way. If the bigger is convergent, then the smaller will converge to. Case 2. If the summation of un diverges, then the summation of un will diverge to. You can think it in this way. The smaller diverges, which means it is not bounded. Namely, the bigger one will diverge to. In order to explain the above ideas and methods clearly, now we will give you the concrete proof process. Let sigma be equal to the summation of Vn. According to the given condition, un is less than or equal to Vn. Then the partial sum Sn is u1 plus u2 plus un. The sum is less than or equal to V1 plus V2 plus Vn, and pay attention to the given condition. The summation of un is convergent, which means less than or equal to sigma. That is, the partial sum is bounded. Finally, we have the result like the summation of un converges. Now, we will prove the second result. Let Sn tends to positive infinity, and according to the known condition, un less than or equal to Vn. Then un corresponding to the partial sum Sn, and Vn corresponding to the partial sum sigma n. It is obvious that sigma n is greater than or equal to Sn, which means tends to positive infinity, namely not bounded. Naturally, we get the summation of Vn diverges. According to the above statement, we can get the deduction if the summation of un converges and satisfying the expression Vn less than or equal to k times un, then the summation of Vn converges to, and vice versa. But we can't ignore the disadvantage of comparison method, which means that there must be a comparative series. How to apply the comparative theorem? Now, let's give an example of how to apply this theorem. Please prove the summation of 1 over n to the power p converges if p is greater than 1. Proof given conditions. P is greater than 1. Then we have 1 over n to the power p equals the integral of the constant times dx. Note that the integral variable is between n minus 1 and n, which is less than or equal to 1 over x to the power p with the same integral interval. Namely, if x is between n minus 1 and n, then we have the following expression. Hence, we have the partial sum Sn less than or equal to the corresponding integrals. The corresponding upper limits and the lower limits are 0 to 1, 1 to 2, and n minus 1 to n, according to the additivity of intervals. We obtain Sn less than 1 plus the integral of 1 over x to the power p with the limits 1 and n. After calculation, we get the following result. So, Sn is bounded. We get the following results. Sn is bounded, namely, the p-series is convergent. Now, let's consider another case, namely, p less than or equal to 1, which means 1 over n to the power p greater than or equal to 1 over n. In our minds, we already know that the summation of 1 over n is divergent by using the comparison method. Then p-series is convergent. Now, let's summarize our important series. The first is a geometric series. Pay attention to the result. The absolute value of p is less than 1, then it is convergent. And the absolute value of p is greater than or equal to 1, it is divergent. The second is p-series. P is greater than 1, it is convergent. Otherwise, it is divergent. The third is harmonic series. The summation of 1 over n is divergent, which is critical in the application of comparative theorem. Please understand and try to remember these conclusions. We should master some convergent positive term series as comparison students when use the comparison matrix in our future study. Mark and apply these definitions and theorems as follows. The definitions of the positive term series: bounded sum test, fundamental theorem, integral test, theorem C, and the common comparison series. Let's finish the following thinking question. Please select the series converges. First of all, we notice that this is a positive term series. Our purpose is to select the partial sum Sn is bounded according to the factor n factorial equals 1 times 2 times 3 and satisfying the expression. So we have 1 over n factorial is less than or equal to 1 over 2 to the power n minus 1. Thus, the partial sum Sn is less than or equal to 1 over 1 plus 1 over 2 plus 1 over 4 and 1 over 2 to the power n minus 1. This is an equal ratio series. According to summation formula, we have 2 times 1 minus half to the power n. Obviously, this expression is less than 2. by the bounded sum test, we will know that the given series converges. Thank you for your listening. See you next time.